everyone. My name is Mario Keiko. I am a biostatistician at Beth Israel Deaconess Medical Center. And today it is my pleasure to give my talk about diagnostics that we need to be aware of when running linear regression models. I have no conflicts of interest to disclose for this presentation. So, as most of you are already aware of, research is a process, and it is a process that usually follows the first step of first defining the research hypotheses. Then, based on the research hypothesis that we defined, we design the study, we conduct the study and collect the data. Then we run the statistical analysis based on the data that we collected and on the research questions that we are trying to answer. And finally, we synthesize the statistical analysis results and share the findings. When it comes to statistical analysis, among many points that we need to be aware of is that usually you need to start with first the descriptive analysis of your data. You need to, when you get the data, you need to start exploring what the data looks like and also take a look at possible data issues such as the presence of missing data or the presence of data entry errors. This is the crucial steps that will help when you later try to do some modeling with your data to answer the research question. And another important part of the statistical analysis is statistical modeling, which could have two different focuses. The first one is we try to do inferences, where we try to draw conclusions about the unknown population parameters based on the sample that we have collected. For example, we try to say, based on the sample that we have, what are the factors that are influencing the risk of type 2 diabetes? And this is a question where we are trying to make inferences based on the data that we are collected about the broader population where the data came from. The second part is that we could try to do prediction with our statistical analysis. Basically, we try to predict the outcomes in the data. And the relevant question that could be answered here is, can we accurately predict the onset of type 2 diabetes given patient characteristics? So in order to do statistical modeling, either it be for making inferences or a prediction, a very powerful tool is linear regression model. The objective here is that we try to study the relationship between independent variable or variables x and the dependent variable y, where y is the continuous variable. And this kind of model can be used both for estimating the relationship between the independent variable or variables x and the dependent variable y, but we can also do prediction, basically try to predict y given the observed values of x. The simple linear regression is written in this form where we have the y that is being equal to beta 0, which is the intercept of the model, plus beta 1, which is the slope of the line, multiplying the values of x, plus some error term. And when we have our data, basically we have only these points. And what we are trying to do through the use of the linear regression model, we are trying to find the best fit line that best kind of describes the relationship between x and y. But how do we find this best fit line? Basically, we find this best fit line by trying to minimize the distance of the data points from this best fit line, and that would be that would determine our linear regression model. When it comes to determining the best fit line, given our data, we could have something like this. Clearly, you can see that the distance of the points from this line that we are thinking that best describes the data is much more higher than what we had before, and therefore this would not really be the line that best describes the relationship between x and y in our data. We could also have something like this, where we see that we have started to minimize the distance between the points and the line. However, it is still high. And lastly, when we try to minimize the sum of the squared errors, basically we take the distance from each of the points, from each of the lines that we try. We aren't, it's not us trying, but like the software is trying to find. And we try to minimize that, and that determines our best fit line. And once we have found that, we, based on that best fit line, we can estimate the terms of the model where we have the beta zero, which is the intercept. Basically, it describes what is the value of y when x is zero. And we also have the beta one, which is the slope of the line. As you most likely already know, this describes what is the increase in y for each increase in x by a certain amount of units. And lastly, the last component that is in the model is that error term, which is the distance of the data points from the best fit line. Here I use the epsilon term, which describes the theoretical distance, but later on we will see that this is something that it's actually realized, that we measure and that we call residuals. But we'll talk about that later on. So when it comes to the linear regression model, it can take multiple forms. For example, we could have a simple linear regression that we saw already, where we have only one independent variable and we try to see its relationship with the dependent variable y. We could have multiple linear regression model where we have more than one independent variables. We could also have polynomial linear regression, where for some of the variables, the relationship is not between, for example, the variable x2 and y, but it is between the squared x2 and y. There are multiple other forms, but for now, as a general presentation, this should be okay. And the reason why I presented those multiple forms of the linear regression model is to show that it is actually a very flexible tool. We can account there for many variables in our data. We can account for different relationships between the x and y. As we saw, we had squared x being related here to the dependent variable y. In addition, the linear regression model is a popular tool because it is available in a broad range of the statistical software packages. It is also very easy to interpret and robust and efficient. And let us look at how we would interpret the results of a simple linear regression model. Let's say that we have collected data on the cholesterol level and the HbA1c measures for some sample that we collected. And we're trying to see whether there is a relationship between HbA1c and the cholesterol level. For that reason, we fit this regression model, which after we estimate, we get the coefficient estimates. So from that, we have the beta 1 coefficient, which are represented by this estimate here, the standard errors that correspond to them, the statistic, and the p-value. And here of interest for us is to see the relationship between X, which is our HbA1c, and the cholesterol level. And based on the beta coefficient, we can say that for each increase in HbA1c by 1, the cholesterol level increases on average by 25.146 milligrams per deciliter. And further on, the effect is statistically significant with a p-value of 0.002. However, we just getting the data, running the linear regression model, and interpreting the results is not enough. We need to run the diagnostics for the linear regression model in order to verify that they are met and therefore that our results are valid. For that reason, we need to go through these steps to verify the assumptions of the linear regression model. And the assumptions are linearity, independence of residuals, homoscedasticity or the constant variance of residuals and the normality of residuals. Notice that I have put in bold the residuals because usually when we try to evaluate whether the assumptions are met, we base that conclusion on the residuals and their distribution. Even the linearity, even though it's not mentioned here, can be assessed based on the distribution of the residuals. So for assessing whether these assumptions are met, we can run formal statistical tests, and a broad range of statistical packages have made them available for us, and they are easy to use. However, we need to keep in mind that this test can be influenced by the sample size, meaning that if we have a sample size of, let's say, 10,000, and we try to run a statistical test where we are trying to say whether, for example, the normality of the residuals assumption is met. Even if we have small deviations from the normality, the fact that we have 10,000 data points is going uh, to make our result be statistically significant, and we conclude that the linearity is not met. On the other hand, if we have a small sample size, let's say only 25 observations, we run the test for normality of residuals and we find it to be non-statistically significant, and we conclude that the linearity assumption is not violated. Even if we were to look at it, there could be high deviations from normality, and we are going to see later on. And that is the reason why usually it is suggested that we use graphical displays in order to verify whether the assumptions for the linear regression are holding. This is because in addition to them being a very powerful tool in detecting the violation of these assumptions, they can provide insights for the presence of issues. And based on these insights, we can consider next steps about how the violations can be resolved. So let us look at each of these assumptions one by one. The first assumption is linearity. The linearity assumption states that there is a linear relationship between the dependent variable and the dependent variable or variables. As the first step, you can start to look at the linearity assumption just by doing a scatter plot of your x and y variables and try to see whether you can more or less fit a straight line between them to describe their relationship. However, in terms of the linear regression, this can be evaluated by the fitted versus the error plot. And here on the left side, I am showing what that plot would look like. On the x-axis, we have the fitted values, and on the y-axis, we have the residuals. And we are trying to, with this red line or red smoothed line, we are trying to see what is the relationship between the fitted values and the residuals, and we see that it is more or less flat. That tells us that there is really no relationship between the fitted values and the residuals. We have points scattered across around that line, and we do not see any pattern that is obvious for this data. And that's why we can safely conclude that the linearity assumption does not seem to be violated here. On the other hand, on the plot on the right, we see that this is not the case. We see that there is a relationship between the fitted values and the residuals, which could be described by a parabola. It is not flat, and we see that there is a pattern for the relationship between the fitted values and the residuals. These, in addition to helping us identifying that we could have an issue with the violation of the linearity assumption, gives us some insight about what kind of relationship that could be. And in this case, we could consider trying to do some kind of parabolic association between x and y, and most likely it is going to address this issue. In addition to basing some adjustments for our regression model on what we see from the residuals versus fitted plot, we could decide to do some transformation of the data. For example, taking the logarithm of y. We could consider to do a polynomial regression, which in this case trying to see the relationship not between y and x, but between y and squared x. We could consider including some interaction terms in the case when we have two or more independent variables. And also, if the linearity assumption still is not holding, we could consider running nonlinear models. Next comes the independence of residuals assumption. This assumption states that the residuals should be independent. And usually we have a problem with this assumption when we have multiple measurements coming from the same individual. For example, we measure at multiple time points the cholesterol level from the same individual. And here it is reasonable to think that since the measurements are coming from the same individuals, they are likely to be correlated with each other. And that's why it is reasonable to suspect that the independence assumption for the residuals is not met. In the case when this assumption is not met, usually there are very specific kinds of data, as we mentioned here, like time series data or multiple measurements coming from the same individual. We could try to do alternatives to linear regression, such as doing time series modeling or trying to implement mixed models. The next assumption is the equality of variance. What this assumption states is that the spread of the residuals should be approximately the same across different levels of the independent variable or variables. And in this case, we refer again to the fitted versus residuals plot. And we want to see that we have approximately the same spread across different levels of the fitted values. So I am using the plot from before. What we see here is that the spread at fitted values of 190, let's say, is more or less the same as the spread in the residuals in fitted values of 140. And that's why we can conclude safely here that there does not seem to be evidence that there is an indication of the violation of the homoscedasticity assumption. And here I included these lines just to show that like the spread seems to be more or less the same. However, we could also have a case like the plot on the right, where we see that the spread is relatively low at the low fitted values for x, for the x-axis. However, as the fitted values increase, we see that the spread of the residual starts to increase. And in this case, it is reasonable to suspect that we have a violation of the homoscedasticity assumption. And in this case, when we detect that there is a violation of this assumption, we could try to do some transformation of the y variable, or we could also try to do a robust estimation of the standard error. This is because the homoscedasticity assumption violation usually influences the estimates of the standard error. And with us using a robust estimation of the standard errors, we could try to start addressing this violation of the homoscedasticity assumption. Next assumption is the normality of the residuals. This assumption states that the residuals should be normally distributed. Now, the reason why I have highlighted residuals here is that often researchers state that we need to have the dependent variable or the y variable to be normally distributed. However, this is not really the assumption for the linear regression. The assumption is about the distribution of the residuals of the model. And we can evaluate whether this assumption is violated through the histogram of the residuals that we get from the model, also QQ plot, or where we expect to see that the points should fall approximately on the diagonal line. And I'm going to demonstrate what the QQ plot and the histogram would look like if the normality assumption does not seem to be violated. So in the QQ plot, in this plot here, we see that the residuals follow more or less this straight diagonal line. That's why it doesn't seem to be that we have an indication of the violation of this assumption. In addition, the histogram of the residuals seems to follow more or less a normal bell-shaped distribution. However, in the plot on the right, we see that the points for the standardized residuals clearly do not follow a straight diagonal line. And that's why here we have evidence showing that the normality of residuals assumption could not be holding. In addition to these graphical displays, as we mentioned before, statistical softwares offer formal statistical tests like the Kolmogorov-Smirnov test, which basically test the hypothesis that the residuals are normally distributed when that hypothesis or the p-value for that hypothesis is less than 0.005 or a threshold that we choose. Then we say that there is evidence that the normality assumption does not hold. However, when using this kind of test, we need to be aware of the implication of the sample size and the power of the test. That's why, as we mentioned before, the graphical displays are a better indication of whether the assumptions are not met. And as you may have noticed, for the plots here, I have used R to generate them, but any kind of software that you are using, it should be pretty straightforward for you to find out how you can generate this kind of displays just by having in mind what assumption you are trying to test and trying to find out how you can generate these displays for your model. Now, this covers what would be the assumptions that you need to check for when running a linear regression model. There are a couple of extra points that I would like to cover. And the first one is that I would advise to avoid transforming continuous variables to binary or categorical variables. Why this is so, it is that you have already spent so much time and effort trying to collect your data. And if you have collected a continuous variable and you try to turn it into or transform it into a categorical variable, basically you are losing information. And with this comes the cost of also losing statistical power. And in addition, the cut points that are used for turning or transforming a continuous variable into a categorical variable could be arbitrary. And to demonstrate this, I refer to this paper where what the author did is that he created 5 scenarios. These 5 scenarios are very distinct from each other. However, when you use the cut point of using the mean of x and the mean of y to turn your variables into binary variables, you get exactly the same 2 by 2 table where you have 25 observations in each cell. If you were to say whether there is any relationship between x and y, you would conclude that there is no association between x and y. However, we can clearly see here that there is some kind of association that is not the same across the different scenarios. And that's why this is the demonstration that shows why the transformation of continuous variable into binary and categorical variable would come with the cost of losing valuable information and even hiding relationships that are really in the data that we are missing. The next extra point is the issue of multicollinearity. We say that there is multicollinearity for our regression model when we have 2 or more independent variables that are highly correlated, and therefore they have an overlap in the information that they are providing to the model, or they provide redundant information. With the presence of multicollinearity, the model may not be able to estimate the individual effects from each independent variable, and also may come at the cost of inflated standard errors. How do you diagnose the presence of multicollinearity? You start with the bivariate plots, and that's why the exploratory analysis, or also what we describe as descriptive analysis, is very important, because this is going most likely to show that there is a strong relationship between any 2 pairs of independent variables. The next tool that you can use is the variance inflation factor, which basically gives you a hint of whether there is a multicollinearity issue in your model and which variables comes with with the multicollinearity issue. Usually, researchers try to use some rules of thumb when it comes to the variance inflation factor, where for any variable that you have a VIF of a greater than 5 or 10, you suspect that there is a high multicollinearity. Now, once you diagnosed it, how do you work around it? You can start by dropping correlated variables, basically keeping in the model the variables that are the primary interest for your analysis and dropping other variables that you are trying to adjust for, but which create the issue of multicollinearity. You could try to combine variables with each other or also use penalization methods such as ridge or lasso regression. The next extra point that is important when we run a linear regression model is trying to identify influential observations. We call influential observations data points that have a large impact on the estimated coefficients. And in this case, we identify three kinds of points. We identify outliers, where we have a data point where the response Y is unusually high or low. We have high leverage, where we have a data point that has extreme predictor values or in the combination of the predictor values, and also high influence, where the data point has a high impact on the coefficient estimate or on the model fit. If removed, then the model would change substantially. Here we need to point out that the outliers and the high leverage points have the potential to have a high influence in our model, but they may not necessarily be the case. We diagnose the presence of influential observations by some tools that are also available in the majority of the statistical softwares, such as the Cook's distance, the difference in the fits, or the difference in the beta coefficient estimates. And once we have diagnosed this issue and we found that it is present, we need to carefully investigate whether these are real outliers or real data for our project. For example, it could be that we have a person recorded with an age of 500, and our model finds that it is an influential observation. Of course, if we were to check, we would think that a person with an age of 500 is not really biological plausible, and that's why this could be considered as a data point that we remove. However, we also need to be very cautious about removing data from the model. First is because we have spent valuable resources to collect this data. And second is that by removing data from the model, after making sure that these are real data that are collected from our sample, by removing them, then we run the risk of decreasing the generalizability of our model results, because an influential data point, while it is influential for our model fit, it could describe a real phenomenon that is happening in the real world. And next, what I'm going to do is I'm going to show a couple of scenarios for this kind of situation. The first one is where we have no outliers and no high leverage point. Basically, we are looking at the relationship between X and Y, and we see that we can fit more or less a straight line between X and Y. And it doesn't seem that we have any observation in X that is unusually high or low, or any observation in Y that is unusually high or low, or also unusually high or low, given the values of X. Next, we look at a situation where we have an outlier, but it doesn't have a high leverage. So in this case, we have this red dot here, where we see that it is very out of range from the best fit line. Basically, what this is saying to us is that the measured value for Y is unusually high given their value of X. However, we need to point out that this point does not have a high leverage, which means that its corresponding value of X really falls within the range for the observed X values. What we do is that we try to see whether this point can be an influential point for our model. And we fit both kind of model, the straight line with the point being there and the dotted line by removing the point that we suspect to be influential. And we see that the estimate of the beta 1 coefficient, which is of interest to us when describing the relationship between x and y, does not change substantially. So with this, we can conclude that there is no indication that this red dot here has a high influence on our model fit. Next, we look at a situation where we have a point that is not really an outlier, that has high leverage, but is not influential for the model fit. Basically, we have more or less the same data points as before, but now we have a red dot that is first unusually high for given the range of the rest of the values in X. That's why we conclude that it has a high leverage. However, it falls more or less within the best fit line, basically saying that while it is high given the rest of the values in y, it is not unusually high given the value of x. And that's why this doesn't seem to be really an outlier for the y values. And in addition, we see that it is not influential. When fitting the model straight line with the red dot and the dashed line without the red dot, we see that the estimate of the coefficient fit does not change a lot. And that's why here again, we conclude that this point is not really influential for our model fit. And lastly, we could have the situation where we have a point that is both an outlier and has a high leverage and also has the high influence. So in this case, what we see is that first, the red dot has a high leverage, basically like it is very out of range given the rest of the X observed values. In addition, it is also an outlier. It is very out of range from the line of best fit, and while the X value is unusually high, the Y value is unusually low. That's why we conclude that this red dot is an outlier. And lastly, we see whether it has a high influence. We have the straight continuous line that is the model fit with the red dot being there, that has an estimate for the beta 1 coefficient 3.32. And then we take the red dot out and we fit the model, which is represented by the dashed line. And we see that the beta 1 coefficient there is 5.12. And with this, we can safely conclude that this data point is a data point that has a high influence on our model fit. And that's why we need to investigate further what is going on with this and what are the strategies that we're going to do to mitigate or explore further this issue. So this concludes my talk, and I would like as the take-home messages from the presentation to be that, as we already know, the linear regression model is a powerful and robust statistical model that is very easy to use and easy to implement. However, in addition to us fitting the model and interpreting the model findings, it's very important to assess whether the assumptions of linear regression model are met, because this is what determines the validity of our model. And for this, the graphical display is our powerful tool. Also, we need to keep in mind that in addition to verifying the assumptions of the linear regression model, we need to do an assessment of the multicollinearity and the presence of influential observations and the strategies that we are going to pursue to address them. And with this, my presentation is concluded. I thank you very much for your attention and sharing here my contact information in case you need to reach out to me for any question that you may have. Thank you.